Welcome back to the Engineering Systems channel. Over our last few explainers, we've been on this massive mission together, right? We've been building out a truly resilient architecture for FoodDash. We've laid down a ton of groundwork, but today is where things get genuinely interesting.
Let's put you in the hot seat for a second. Imagine you are the CTO of FoodDash. You've got a hungry customer asking, hey, can I place an order literally whenever I want? You've got a restaurant owner stressing out, asking, are my orders going to keep flowing in during the Friday night dinner rush? And of course, you've got your investors sitting there asking, so exactly how reliable is this platform? Suddenly, just shrugging and saying, it's mostly available, just isn't going to cut it. They need an exact number. We know our system can survive failures now, sure, but how much downtime is actually acceptable?
Okay, before we dive into the math, let's just quickly reorient ourselves with the robust FoodDash setup we've already built. Remember, we totally eliminated those single points of failure. We brought in redundant servers, we spun up replicated databases, and we set up health checks with automatic failover. Basically, our system can catch a failure and bounce back all on its own. But before we go adding even more moving parts to this beautiful architecture, we really need to put a hard number on what reliability actually means.
And that brings us to availability targets. In simple terms, an availability target is just the percentage of time that a system stays completely operational. When engineers sit down to actually measure this reliability, we almost always talk about a concept known as the famous nines.
Let's start the drumbeat. First up, we have the baseline tier, 99% availability.
Then we slap on an extra 9, taking us to 99.9%.
We add yet another 9, and we hit 99.99%.
And finally, we arrive at the absolute holy grail of reliability metrics, 5 nines, 99.999%.
Now, looking at those numbers side by side, they seem incredibly close, right? Like a fraction of a percent difference, almost identical. But here's the catch. They hide a massive, and I mean massive, difference in the amount of real-world downtime your system is actually allowed to have.
Let's break this down into actual physical time. Imagine FoodDash is running non-stop for an entire year. At 99% availability, you are allowed roughly 3.6 days of total downtime. Think about that. You could be totally offline for a long holiday weekend, and technically, you'd still hit your target. But watch what happens when we add just one little 9. At 99.9%, your allowed downtime shrinks down to about 8.7 hours per year. Push that to 99.99%, and you get roughly 52 minutes for the whole year. And if you're chasing those legendary 5 nines, you are allowed a mere 5 minutes of downtime annually. Seriously, just 5 minutes for the entire year?
Now, what's really wild here is how incredibly steep the margin for error drops off with every single additional 9. Just look at that collapse. We are literally going from measuring our downtime in entire days, dropping sharply down to hours, and then almost instantly plummeting down to just minutes. It's like falling off a cliff.
This incredible, shrinking window of time introduces a concept we like to call the cost of perfection. Because while every extra 9 might sound like this tiny, almost negligible fractional improvement on paper, in reality, it creates a ridiculously challenging and incredibly expensive engineering problem.
Just to chase those extra 9s, let's watch how our FoodDash architecture has to balloon in complexity. We always start out with a single server, right? It's simple, it's cheap, but to bump up that availability, boom, we have to stack on redundant servers. Then we need load balancers to manage them, then replicated databases, then these super complex automatic failover systems. Eventually, to get those last few 9s, we're literally forced to deploy across multiple availability zones and completely different geographic regions around the world.
The absolute crucial takeaway here is that availability is never ever free. Every single additional 9 you want means adding more infrastructure. You need way more monitoring, significantly more automation, endless testing, and, let's be real, a lot more specialized operational expertise from your engineering team. The closer you try to get to perfect uptime, the harder and astronomically more expensive every tiny improvement gets.
Which naturally leads us to pivot away from the pure engineering side and face a pretty stark business reality. Ask yourself, does every single system actually need 5 nines? Is taking on this massive extreme cost and skyrocketing complexity always justified for every app you build?
Usually, not even close. Just look at this contrast. If you've got low-stakes systems, say an internal reporting dashboard or a company wiki, 99% availability is absolutely fine. Like, you really don't need a multi-region global failover setup for the company wiki. But for high-stakes systems, things like a payment processor, an emergency response network, or the core FoodDash ordering platform itself, those definitely push toward 5 nines simply because even a minute of downtime there directly impacts huge amounts of revenue or user safety. At the end of the day, picking the right availability target is totally a business trade-off, not just an engineering puzzle. So, let's quickly wrap up our main takeaways for today. Remember, availability targets are just how we measure our operational time percentage. Stacking up those extra nines shrinks your allowed downtime dramatically, pulling you incredibly fast from days down to mere minutes per year. And most importantly, approaching that perfect uptime causes an exponential soaring growth in both your costs and your system complexity. It's always about balancing the engineering math with the actual business reality.
All right, so we've nailed down our targets, and we've got all these multiple, healthy, highly redundant servers up and running. But wait a second, there is a catch. Now that we've built out all this sprawling infrastructure, we actually need a way to distribute our user traffic efficiently across it. I mean, think about it. If FoodDash has a whole cluster of multiple healthy servers, how does it actually decide where the very next user request should go? How do we stop one server from totally melting down from overload while the others are just sitting there perfectly idle? Well, that is exactly the puzzle we are going to tackle next. Thank you so much for hanging out and watching Engineering Systems today. Be sure to subscribe so you don't miss out, and I will see you in our next explainer.